So good morning, everyone. My name is Kangyu. Currently, I'm a postdoctor from Kyoto University, and today I will give this talk on behalf of Oscar. The title is Structural Exploiting and System-Theoretic Optimization for Local Control with Discrete Events. And in this talk, I will introduce several optimization-based control methods from our lab. And this kind of methods are designed for local systems with discrete events. Let me start with the problem setting of optimization-based control. And in this framework, we formulate the control problem as a mathematical problem called optimal control problem, or OCP. And the OCP minimizes a cost function while subject to the dynamical system. Here we clarify the dynamical system based on the continuity of the state. For smooth system, the state and its time derivative change continuously. So the system only has continuous events. While for non-smooth system, the state or its time derivative may be discontinuous. And this discontinuous appears when the system switches from one mode to another mode. And we call this mode switch or discrete events. And in this talk, we only focus on non-smoothness came from internal state-dependent vector. And in real-world application, optimization-based control is often used in a receding horizon manner to achieve feedback control. And this method is called model predictive control, or MPC. At each control period, we solve a parameter OCP. Then the first control input is applied. Our group has developed several numerical optimization-based methods for MPC of smooth system. Here I will review them in two categories. The key ideas are quite general, and they will also appear later for the optimization method for the control of non-smooth system. And the first category is structure exploiting optimization. The main idea is to use the OCP structures to improve the computation efficiency. So for example, the OCP has a time stage structures, and this lead to some temporal sparsity, which can be exploited by parallel method. And also for larger scale OCP, we have a spatial sparsity, and this kind of sparsity can be exploited by Jacobi-type method. The second category is the system theory optimization. This type of the method does not directly solve the optimization problem. Instead, it views the control sequencing as the straight trajectory of a continuous time dynamical system. Then we obtain the control input by some efficient approximation method for the dynamical system. And this method has been successfully applied to a real-time BC. For example, the parallel method was applied to task checking control of a KUKA robot, and the Jacobi-type method was applied to the temporal true control of a PDE system. And the CGMS, which is the system theory optimization method, has been applied to Hescopo with fair rotor and Kawasaki vessel. This example shows that structural exploiting and system theory optimization are very effective for smooth system. So, now we move to the non-smooth system. And as mentioned before, non-smoothness came from discrete events. And these events are useful because they can describe rich logical behaviors and physical interactions. However, these events also make the optimization problem much more difficult. One classical approach to solve the resulting optimization problem is the methodological programming, or MIP. And this kind of method encoded the discrete events explicitly by some individual variables. And this requires some branch and bound search tree computation. So it can be accurate, but not very scalable and can be inefficient. And in contrast, another approach is nonlinear programming. And this kind of method model the discrete events implicitly by some continuous variable. This can lead to some sparse linear algebraic computation. And with dedicated algorithm, it can be scalable and efficient. So our talk will focus on the second direction. And in this talk, we consider three discrete event representation using continuous variable. The first one is event sequencing representation. Here, the event sequence is given, and the system can also be optimized as well. And the second one is signal temporal logical representation, or STL. And here we use a robustness function to describe the satisfaction of the STL formula, which used to model some discrete events. And the third one is equilibrium constraint representation. And here we have some variables which are governed by a variation equilibrium that describe some equilibrium phenomenon such as friction contact. And the key point is that each representation reveals unique structures, and this kind of structures can be exploited by optimization algorithm. And the rest of the talk is organized into three parts. And for each representation, we develop a corresponding structure exploiting optimization algorithm. And for the last part, equilibrium constraint representation, I will also introduce a system theory optimization method. So we start with the first part, and this part is based on the work by Dr. Katayama and Professor Oscar. So why do we consider event sequencing representation? And in many robotic tasks, the system switch between different modes. So for example, jumping motion of a quadruped switch between standing and fighting modes. And the event sequencing of this mode can be provided by a higher level planner or a perception pipeline. And once this event sequence is given, the non-smooth ODE can be written down as a multi-phase ODE. And then there's no combinatorial structures in the optimization problem. So the resulting problem became a standard NLP. And for this representation, the resulting optimization problem is a multi-phase OCP. And each phase has its own dynamics. The switch time and the time state can also be optimized as well. After the multiple shifting discretization method, we can obtain a standard NLP with a structural sparsity. And when we solve this NLP by some Newton type method, we found that the calculated matrix has a broad diagonal sparsity. And the key point is that optimizing the switch time and the time state does not destroy this sparsity. And therefore, we can the recursive recursion can still be used efficiently. And in robotics, this is also known as ILQR or DDP. And for the recursive recursion, I will not discuss the technical detail. So instead, I will explain its key idea from two different perspectives. The first one is the dynamical program perspective. In the backward recursion, we construct a cost-to-go approximation to summarize how the cloning action affects future costs. And in the forward recursion, we solve a QP and get the prior digression. And the second one is the linear algebraic perspective. In the backward recursion, we perform broad Gaussian eliminations. And this will transform the broad diagonal system into a broad low diagonal system. Then in the forward recursion, we solve the linear system stage by stage. And recursive recursion is very promising because the computation cost grows only linear with respect to the horizon. And for this representation, our group has developed many other structure exploiting algorithms. And these algorithms are integrated into an open source software called Robotalk. This software provides efficient optimal control solver for robotic systems with context. And here I will not go into the details. You can find more information in the GitHub page. And we compare robotic MPC with and without switch time optimization. And we can see that optimizing the switch time improves the physical visibility of the trajectory. And the robot motion became more consistent with the contact events. And this method is also broadly applicable. It was tested with different kinds of the event sequence and robotic systems. And finally, this method was demonstrated on how experience using the unitary quadruped. And for different cases, this method successfully achieved 0 kHz real-time PC. And this completes the first part. The key message is that for a given, if the event sequence is given, then we can remove the combinatorial structures in the optimization problem. and we can still exploiting the sparsity by the recursive recursion. And also optimizing the switch time helps improve the physical, improve the trajectory visibility. And now we will move to the second part. So in this part, we focus on the signal temporal logical representation, or STL. And this part was based on the work by Takayama, Professor Hashimoto, and Professor Osaka. So what is STL? STL describes the discrete events in a trajectory using some temporal and logical operators. So for example, STL can describe different kinds of the logical path planning using this operator. And to use STL in optimization, we introduce the robustness function. And this is a real value function that measures the certification of a STL formula. A higher value means stronger satisfaction, and a negative value means the violation of the formula. And this function is defined recursively from predicators. These predicators represent basis events, and the temporal and logical operators are defined by min and max functions. So STL gives a min-max representation of discrete events. Here is the OCP with the robustness function. Here we have the cost encourage stronger satisfaction of STL formula, and the inequality constraint ensure that the STL formula is satisfied. And the challenge is that the robustness function is highly non-convex and non-smooth, and this came from the min and max composition. So one approach to solve the STL constraint OCP is the mixed integer programming, and but it relies on the search tree computation, so it is not very scalable. And another approach is the nonlinear programming method, and this kind of the classical method is to smooth all the min and max function, but this can give a cost approximation and still highly nonlinear. And the contribution of this was to review and explore the convexity and cheese structures in STL. This is done by two steps. The first step is a structure-aware decomposition to review the convexity in the STL formula, and the second part is a check-web plenty method to solve the resulting optimization problem. And I will start from the structure-aware decomposition. So the difficult part is the robustness function. And instead of smoothing the whole robustness function, we make a decomposition on these min-max expressions. Then we smooth only the min part. So the first step, we remove the outermost operator by a series variable. Then we continue the decomposition on the sub-formula until we reach the predicators. This gives a set of simple constraints. The max part gives the convex constraint, and the min part gives the concave constraint. And these concave constraints are smoothed by the Meroving function. And finally, we can obtain a optimization problem called difference of convex programming, or DC programming. And here the key message is that we have there still have some convexity structures in the STL formula, and this can be reviewed by some structure-aware decomposition. And after we obtain the DC programming, we aim to solve this problem. And the standard approach is the plenty convex concave programming, which penalize the constraint violations. Here it realizes the inequalities and only linearize the concave term at each iterations. But the problem is that the STL formula has tree structures. And for example, the constraint near the top of the tree can affect much more sub-formulas. So they should be treated with a larger weight. And this motivates the check-web plenty CCP. And the theory also supports this framework. We studied the property of the robustness function and the DC decomposition. You can find more detail from our paper. And finally, we have some numerical experience. We have a comparison experience include the proposed STL CCP and the GroupB MIP, and also the SN of NLP. And here, Sn of NLP smooths all the mean and max operators. The scenario is the logical path planning. The robot will require that the robot first reach either one of two regions, B1 or B2, and it always avoid obstacles. And finally, it will reach the goal. So the result shows that the proposed method gives better scalability compared to MIP. And also we had a shorter computation time and a higher STL robustness, which means better certification of the STL formula. And we also provide satisfactory trajectory for different scenarios. And this completes the second part. So the message is that STL has both complexity and cheese charges, and these charges can be exploited by convex optimization. So now we move to the last part. So this part focuses on the equilibrium constraint representation. Here I will introduce two methods. The first one is charger-aware, it is charger-exploding optimization, and the second one is system-theoretic optimization. So this work is supporting. This is my work. And so first, what is equilibrium? So equilibrium problem is to find a state where no agent, force, or variable has a incentive or tendency change. For example, physical economy means force balance, while for economic equilibrium means balance between benefit and risk. And a general mathematical framework for equilibrium problem is the variation equality, or VI. It is defined to find a point that satisfies infinitely many inequalities of this form. And geometrically, the vector f forms a non-obvious angle with every feasible digression. And a VI may have multiple solutions, so each solution may activate a different set of inequalities. So in VI, the discrete events can be understood as the selection of active inequalities. And VI also include many important examples such as complementary problem and constraint optimization problem. So this is the OCP with equilibrium constraint. The dynamics depends on an algebraic variable lambda, and this lambda is governed by an equilibrium condition. So this formulation is very general but difficult. The first challenge is that we do not have any feasible interior point, and because of this, standard LP may fail. And one approach is plenty measures. But for this kind of feasible region, plenty functions are non-convex, and we need to globalize this non-convex function. And another approach is relation measure, but the relation NLP becomes increasingly difficult as the relation parameter goes to zero. So in this part, our contribution addresses these two challenges. For the first part, we propose a convective exploding method, and this method will exploding the convective charges in a class of plenty function. And second, we use a system theory optimization method to solve the result, to solve the related NLP. And first, let's look at the plenty method. So here we consider OCP with complementary constraint. And this kind of constraint can represent switch case discrete events. To solve this problem, we construct a gap plenty method. Here we use a dgap function to measure the complementary variations. This function is non-negative, and it is zero if and only if the complementary condition holds. So we add it as a plenty term. And this function is semi-smoothly differential and non-convex. So this kind of differentiability means that the Hessian information is available. And our contribution is to review and explore the convective structures in this function. So these structures are reviewed by the partial separability, which means that the function can be written out as the sum of subfunctions. And using this property, we found that the Hessian of this subfunction is positive semi-definity in the green region. And also the capture and the convexity region are controlled by the parameter A and B. So based on this observation, we explore the convexity by exact attribute Hessian regularization. Here we present the Hessian information in the green region, and we only regularize the Hessian in the blue region. So this kind of method is cheap because it only uses the parameter A and B and do not require any matrix factorization. And finally, we look at the system theory method. So here we focus on OCP with equilibrium constraint, and a common approach is the relation method. By some relation formulation, we can obtain a less OCP, but this kind of problem is increasingly difficult to solve. So our idea is not to solve this problem directly. Instead, we design a dynamical system to check the solution sequencing. And to do this, we first reformulate the relaxed NLP as a parametric submission equations. This can be done by using some complementary function. Then we view the solution sequence as the state trajectory of a dynamical system. And this system evolves along a semi-seamless Newton flow. And we prove that this system has local exponential conversion with some reasonable assumptions. And for the implementation, we only need to numerically simulate this dynamical system. And we have some simulation results. So first we test the measure on the benchmark test. And here we show that the gap plenty measure has a highest probability of being the fastest measure. And we also test in a contact imbalance MPC example. The test is to push the middle boss to a time vary design position. And this is done by controlling the two outer small balls. And the result shows that the gap plenty measure can stabilify the contact sequencing to achieve the goal. And also we have some result for the system theory optimization. And here we test our measure on different kinds of the realized NLPs. And for each continuation step, the computation time was about 50 to 35 milliseconds. And the calculated result decreased linear on a log scale. So this means that we have achieved the local exponential convergence. And also, as a comparison, we use IPO to solve each realized NLP exactly. But this will take 1 to 45 seconds for each continuation step. And this complete the last part. The key point is that equilibrium constraint provide a general representation for the discrete events. And for the plenty measure, we can still expose some useful problem structures like convexity. And for the relation measure, system theory optimization help adjust the poor local convergence. And finally, let me summarize this talk. So we discuss optimization method for local control with discrete events. And there are two main regressions. The first one is structure exploding optimization. Here we explore some useful structures such as sparsity, STLG structures, and convexity. And the second one is system theory optimization. And here we solve a difficult problem by evolving a dynamical system. And the good point is that the problem setting are quite general. We do not make any strict or unreasonable assumptions. And the problem is fast, and the solution method is fast, and with some theoretical conversion guarantee. And finally, I'd like to thank this research for the important contribution to this talk. And here are the references for the background and part one. I will not go into the detail. You can refer to this paper if you are interested. And this is the second part. Okay. And okay, so this concludes my talk. And thank you for your attention. I'm happy to share any questions.